All right. So what are the important properties of each node? So for each node in a binary search tree, if the node is not nil, okay, if n is not nil, then n dot left is the left child. N dot right is the right child. N dot parent is its parent, okay, and just for completeness I will keep the parent of root to be nil. Following the book convention, the parent of root will be kept to be nil, and that's how you would know if a node is a root. Okay, so n dot parent is its parent, n dot key is the key. Okay, and this is all following CLRS convention. Okay, CLRS convention. All right, so now that we have binary search trees, I want to define a few things for binary search trees. Okay, so next step is, let me define the height of a binary search tree. So what's the height of a binary search tree? Well, if you start with a binary search tree, let's say an example like that. I'm not going to show all the nils. I will just try to show some of the nils. All right. Okay. So suppose this is a binary search tree. All right. We define the height of a node as the length of the path. Okay. The length of the path or the length of the longest path from that node to a leaf. So in this case, if you start from the root, the longest path is going to go all the way right to a leaf, or you could go all the way right and then left, same thing. All right, and the length of the longest path is going to be 1, 2, 3, 4, 5. Okay, so many books will differ on whether to count the node itself or not to count the node itself. All right, so in the case of CLRS, I believe the height is simply defined as 1, 2, 3, 4, and you do not take the very last node into account. Okay, you do not take the leaf into account. So that allows us to define the leaf as having height 0. So the leaf has height 0. Okay, this node, let's call it N1, has height 1. Okay, so the longest path can go either way. It has height 1. Okay, for example, let's take node N7. Okay, N7 has height 1, 2, 3, 4. Okay, so how do you define the height of a node? So height of a leaf is defined as 0. Okay, now some books will define it as 1, so be careful there. Okay, be careful. But whatever answers I get you will be off by 1, so we are not going to really worry too much about 1 or 0. Let's just define the height of a leaf to be 0 and start. Height of a node is recursively defined as height, take the height of n dot left, take the height of n dot right, okay, and take the max of these and add 1. Okay, so take the max of the height of n dot left or n dot right, whichever one is larger. So take the max of this and add 1 to the result, and that gives you the height of a node. So for example, the height is 0 at these two leaves, the height is going to be 1 at the node here, the height is going to be 0 at the leaf at the node here, let's call this N3, the height is going to be max of the height of its right child, which is 1, height of its left child, which is 0, so max of 1, 0 is 1, okay, plus 1, so the height of this node becomes 2. Likewise, the height of this node becomes 3. The height of the root becomes 4. Okay. So the height of a tree is defined recursively by defining the height of each node, starting with the height of the leaf being 0. All right. So if a binary search tree has n nodes, okay, how high can the root be? how high can the root be. Okay, and that is defined as the height of the tree. So the height of the tree is simply the height of the root node. So what's the height of a binary search tree? All right, there are two cases. So in the worst case, the tree can be completely unbalanced. What is a completely unbalanced tree? Well, every node just has a single child, okay, which is not nil. So the tree is simply almost like a linked list. So it's almost like a linked list. Every node just has one child, which is an internal node. Another child is nil, except for this node, which has nil and nil. So 1, 2, all the way to n. Okay. So in this case, the height of this tree is going to be 1, 2, 3, 4, all the way to n. So height of the tree is going to be n, which is the number of nodes. All right. This is the worst case. What's the best case? The best case is a completely balanced tree where every node has two internal nodes, except for the nodes at the very end, which are going to have two leaves, okay, nil, nil. Okay, so this is going to be all the leaves. So if there are n nodes, what is the height of this tree? Okay, so if there are n internal nodes, n circles, how high can this tree be? Well, we can talk about this. So if there are n internal nodes, okay, so there is one root, two nodes at this level, three nodes at this level, and let's say the height is h. So there are going to be 4 nodes, so 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power h minus 1, okay, where h is the total height of the tree. So what is the equation? Equation is 2 to the power 0 plus 2 to the power 1 all the way to the 2 to the power h minus 1 equals the number of nodes in the tree, number of internal nodes, n, or 2 to the power h minus 1. This is the geometric summation, geometric series. And this sums up to 2 to the power h minus 1 is n, or h is going to be log to the base 2 of n plus 1. Okay, so the height of a tree with n nodes is going to be roughly log to the base 2 of n. Okay, if you want to be precise, it could be ceiling log to the base 2 n, and this is the best case. Okay, so this is the best case. And this kind of a tree is called perfectly balanced. And here, this tree is highly imbalanced, so much so that it becomes a linked list, right? The tree becomes a linked list. What about the trees in the middle? Trees in the middle are going to be somewhere between the worst case, which has to have a height equal to the number of internal nodes, and the best case, which has to have a height equal to log n. Okay, remember there's going to be a plus minus 1 here depending on how I define the base case. All right, I'm not going to be super accurate in this class. So what about other trees? Generally, trees are going to be somewhere in the middle. Okay, so they are going to have some imbalance. Okay, so they are going to have some imbalance. Okay, so they're going to have some imbalance. I'm not going to write the remaining nil. So you can see the tree is imbalanced. For example, the longest path from the root to leaf that defines the height of the tree is going to be something like this. All right, whereas you can see there is another path which is much shorter. All right, so this is going to be imbalanced, not perfectly balanced, not highly imbalanced, but somewhere in the middle. So there is a sliding scale where the height of the tree in the worst case can be n, in the best case can be something like log n, all right, which is a big range to be. All right, so for example, if you insert, for example, n equals 2 to the power 18, which is roughly 1 million. Okay, so if you insert about 1 million nodes, the height can range from about 18 in the best case to about 1 million in the worst case. All right, this is amazing range of heights. All right, and the worst case is when the tree is just a single path. Okay, and in this case I'm just showing everything going to the left. It could go to the left or to the right, but the point being that every internal node here has exactly one internal node children, and then there's one leaf, one internal node which has two leaves. Okay, so and it looks like a straight line tree. Okay, it looks like a straight line tree, or almost like a linked list, Okay, whereas in the perfect case, the tree can be perfectly balanced. Every internal node has two internal node children, except at the very end where it has two leaves. All right. So the height of a tree is going to be very important, because the algorithms we are going to talk about for insertion, deletion, and so on are all going to depend on the height. Okay, so we are going to talk about that in a second.